simply multiplying the g's by a cosine function. So if I think about this bracket right here, what am I going to have there? Well, depending on what n is, right, I'm going to have 1 for my very first value, and then I'll say, all right, cosine of 2 pi over n, and then maybe I'll have a value here that's cosine of 4 pi over n, okay? And I'll go basically through this, depending on what n here, but I'll basically multiply it by a cosine function. The next time through, so this would be j equals 1. The next time through, I'll have j, let's say I go to a later cosine down there, let's say j equals 8. Well then, I'm going to have a function that looks like a higher frequency cosine. So each of these terms, G0, G1c, G8c, is simply cosine, sum of a cosine function multiplied by g of t. And then all added up. This is called a cross correlation. If I were simply to leave this function in time, I'd be cross-correlating the value of the cosine function at that particular frequency with the function itself, and I'd get some kind of output at a particular frequency that was related to the cross-correlation between those two functions. And the cross-correlation measures the similarity between the two functions. So if g of t itself is, say, this cosine function, suppose g of t is it's cosine of 2 pi 8k. Then when I cross-correlate this, I'll get an identity, which will be a big number, right? I'll add it all up and I'll get a huge number because it's always the same. So this is how the Fourier transform, what we call, sifts out cosines of particular frequencies. And there's a very simple relationship between the cosine transform and the inverse cosine transform. And so we can do the operation essentially with the same code. G of, let's call it J, K, is going to be the sum of J equals 1 to n minus 1. And usually there's some scaling factor, 1 over n, and it's G sub J e to the minus I 2 pi over n jk. So here we're summing over frequency to obtain the function back in time. And the only difference here is that we change the sign of the complex exponential. So our basis function is now cosine plus I sine rather than cosine minus I sine. Okay, so that's the math of it. Let's look at, with that math kind of in the back of our mind, let's look at some graphical examples of Fourier transforms from one domain to the other. And then I'll let Nella do her magic with some examples. All right, we are waiting. as we talked about before, if we have a function of time, and in this case, this is a cosine function, right, because it's a maximum at 0, then the frequency transformation is two spikes, one at plus omega, one at minus omega of that particular frequency. Cosine of, why is it there one at minus omega? Well, because cosine of minus omega is cosine of omega. Cosine of minus omega t is equal to cosine of omega t, so it's symmetric. Here's a higher frequency. Notice that the omega value is higher. Here's an example of the superposition of two frequencies. We've got a high frequency and a low frequency. The high frequency is smaller than the low frequency, and so we get a Fourier transform that's the sum of these two. Okay, that's it. So one other quick thing, rather than graphically show this, what I'd like to show is the relationship again between the time domain and the frequency domain. If we have a impulse in time, like a as we talked about earlier, that translates into all frequencies. If we have a boxcar in time, a boxcar is simply a time function that is 0 over short times and long times, and then has value over a certain time. What might this be? What kind of function, what kind of physical action would a boxcar be? Well, if I'm sitting here, right, I turned off the light, so I got a change in voltage. I turned on the light. So the Fourier transform of that is what's called a sinc function, which is defined as sine pi f over pi f. So this is the sinc function, which is the Fourier transform of a boxcar. And the transform is reversible. If we have a sine wave, we actually get an anti-symmetric function in the frequency domain, because sine of minus omega is minus sine of omega. This is our sampling function. This is kind of interesting. If we sample function in time, we also sample something in frequency with 1 over the period of the sampling rate. Okay, so what Nell is going to do is go through teaching you a little bit about mathematics.